Yeah, can I start? Okay. So thank you, Sonia. Good afternoon, and for the people in Europe, good morning, the people in America and Brazil. I would like to start saying thank you to the organizing committee, Sonia, Eurico, Marta, and Ana, who invited me for this talk. So I will talk about the theory of NMR, important aspects to have in mind dealing with low-field instruments. So just to introduce a little bit more of myself, nowadays I'm a professor at University of São Paulo in the city of Piracicaba, that's located in the middle of São Paulo state. Piracicaba is a great city, and it's the oldest, it is home of the oldest agricultural university in Brazil, known as ESALC, that belongs to the University of São Paulo, where I'm dedicated to teach and research in spectroscopy applied to agricultural problems. My main scientific collaborators nowadays are Dr. Luis Alberto Colnago, who was my advisor during my doctorate, and he's a researcher at the Brazilian Agricultural Research Corporation, known as Embrapa, who for decades, his group has been developing high and low methods for agricultural applications, like for food quality, meat analysis, fruits, oil seeds, general materials like polymers, using different NMR equipments, different spectroscopy methods, and so on. Also, the next talk today will be with him. Here at University of São Paulo, nowadays I'm part of a big project about seed science, where we are using several spectroscopy methods to study seeds and related problems, also using low-field NMR. Okay, so in this talk, I will start discussing the basics of nuclear magnetic resonance. Then I will discuss some aspects to have in mind about low-field NMR in the sense of high resolution and low resolution methods. Then discuss techniques and applications. First of all, NMR is a type of spectroscopy, and spectroscopy is the study of the interaction of light or electromagnetic waves and matter. So in chemistry or physics, we have several types of spectroscopy, each one observing different energy levels of the matter, such as ultraviolet visible spectroscopy, infrared spectroscopy for observing the vibration energy level, the rotational energy levels. So NMR is another type of spectroscopy, which is based on the observations of the energy levels in the nuclear spin. So as NMR, in NMR, we can detect signals from hydrogen, carbon, nitrogen, and so on. NMR technique is very powerful for organic chemistry. In NMR, we observe the effects of the nuclear spin, and it has magnetic properties. So you can imagine it as a small magnet in the nucleus of the atoms, as I show here in this illustration. Then we have equipments that measure these magnetic properties to determine different informations of some material. For example, what we call high-resolution NMR is for observe the tiny details of the structure of a molecule, like which atom is bonded with each one, the connectivity. So high-resolution NMR is typically based on these big chemistry laboratories that is a fundamental technique for chemistry analysis with resolution at the atomic level for liquids and solid materials. Then we also have the magnetic resonance imaging technique for applications mainly in hospital or in imaging in general, which is based on the same physical principles of the nuclear spin, However, with some modifications on the equipments to focus in generate an image of the object. Then we also have the benchtop instruments that are mainly used in industry, but also in scientific investigations, like what we call low field NMR, low resolution NMR, time domain NMR, fast field cycling, and also equipments nowadays that have some intermediate spectral resolution. For that are enough resolution for several applications, as we will see. Okay, so let's remember that to observe an NMR signal, you need a nuclei that act like these tiny magnets, or in other words, that have nuclear spin different from zero. Without an external magnetic field in your sample, or B equals 0, you can visualize it as all the nuclear spins as a small magnets pointing in random directions. So the total magnetization here is null, right? When the sample is placed inside a external magnetic field, for example, B equals 90.4 Tesla, the nuclear spins of the hydrogens here will rotate, as I show here, with a precession frequency of 400 megahertz because of this relation, known as the Larmor frequency. In terms of the energy levels, we have two energy levels for spin 1/2, as it is the case for hydrogen and carbon. And that energy levels are represented here by the spins point up or down here. So because of this relation, different nuclei will have different precession frequencies in the same magnetic field. So the next step is to put a probe here, to observe this NMR signal. We introduce the probe here around the sample. This probe is essentially a coil that will apply the pulses of radio frequencies to change the spins from the low energy level to the higher energy level, removing the system from the equilibrium position and observing the system to recover to the equilibrium, we detect the NMR signal. It's easier to understand if we think about the total magnetization in your sample that I represented here with this blue arrow along the z-axis, along the x of the magnetic field. When we apply with the coil a 90-degree pulse in the sample, the total magnetization moves from this equilibrium position at the z-axis to another one, for example, for this axis in the y-axis. This position is not stable, so the magnetization will return to its equilibrium position along the z-axis, and this returns occurs with the precession of the nuclear spins. So what we see is that the total magnetization will precess in this way, and the NMR signal is what we detect in our probe like this, and digitalize the signal that decays in time until 0. Okay, this is called the free induction decay, and processing the signal with a mathematical method named Fourier transform will obtain the spectrum in the frequency domain. Here I show you a visualization of this process of the returning of the total magnetization to the equilibrium position. And here, what we detect as an NMR signal, known as the free induction decay. So let's think, for example, about the ethanol, CH3, CH2, OH. There are three different chemical environments for the hydrogens in this situation. This red one, the green one here, and the yellow one. Because of the electron cloud in each situation, the hydrogen nuclei are more or less shielded than the others. So the effective magnetic field that they are interacting are different. So they have different precession frequencies represented here by these colors. When we detect the free induction decay, all frequency signals are detected simultaneously, as we see here. And the Fourier transform is what makes possible to separate these components like this in the frequency domain, where we can say that this yellow peak represents this group, the green, this group here, and the red one, the CH3. In other words, from the spectra, we can observe the differences in their chemical environment by these chemical shifts observed in the NMR spectrum. Great. So these are the very basic ideas about NMR spectroscopy. But let's see what happens when you analyze the sample, the same sample in a high resolution NMR and in a low resolution NMR equipment. These pictures are trying to show you the differences. Here you see that at a very high intensity and homogeneity magnetic field, you obtain a spectrum with great resolution to analyze the chemical differences in the molecule. However, when you decrease the homogeneity of the magnetic field, the peaks becomes wider and the resolution is lost until the situation here where all hydrogen nuclei are contributing to just one broad peak, as the case in very low field NMR. However, in this situation, you still can obtain interesting information about your sample. Mainly use the relaxometry methods to analyze the relaxation times of the methods and obtain of the sample and obtain informations about the macroscopic properties of your sample. So, when we apply pulses in your nuclear spin, the total magnetization is placed out of the equilibrium state, and this magnetization will return to its equilibrium position. These returns is described by two relaxation processes. The first one is named longitudinal relaxation time, T1, and it's the time for the magnetization to return to the z-axis that is related to the process involving energy transfer from the spins to the lattice. And there's is the second, the transversal relaxation time, T2, that is the time for the magnetization to disappear in the XY plane. This time does not depend on the energy transfer to the lattice, but it is related to the loss of coherency of the magnetization in the XY plane. So the relaxometry methods are based on these relaxation times, and it is described by these exponential equations known as the Bloch equations. The relaxation times are associated, the relaxation times depends on the magnetic environment around the nuclear spins. And it provides information about the correlation times in the molecules that are associated with the mobility of these molecules and the magnetic environment around the nuclear spin. So, as you can see here, liquid samples, typically T1 and T2 are typically here. And for more viscous samples, there are this decrease in the values. And for solid materials, T2 is very small and T1 is high. As this molecular mobility and magnetic environment are related with the presence of other chemicals or structural properties in your sample, the relaxation times can be correlated with macroscopic properties such as viscosity, porosity, moisture, and this is the relation between the macroscopic properties and the relaxation times. So an application that is used a lot by the industry is the determination of the oil content in foods or hydrogen content in hydrocarbons or fuels or water content. And a straightforward way to do it is directly measuring the intensity of a free induction decay, or using a spin echo pulse sequence to avoid dead time or to filter some shorter relaxation components. Where here in the spin echo pulse sequence, the idea is to first apply a 90-degree pulse, followed after some time by a 180-degree pulse to refocus the magnetization and obtain an echo here. Then, after some time, we observe the formation of this echo, and from the echo amplitude, it's possible to calibrate a calibration curve that converts the echo amplitude in the oil content, for example, in some application, or in the hydrogen content in our sample, or several other situations like this. Okay, so to determine the relaxation times, the main two pulse sequences that we use are the CPMG and the inversion recovery. CPMG is based on the applications of a first pulse of 90 degrees here, followed by a trend of 180 pulses, where each one generates an echo, and observing these echo amplitudes that are formating here, we determine the T2 exponential decay curve. Okay, so this is how we obtain the T2 exponential decay curve. And in the inversion recovery pulse sequence, we start with one pulse of 180 degrees, and after a time, we apply a 90-degree pulse to acquire a feed. Changing this time interval here between the pulses and repeating it several times, we obtain this T1 exponential growth curve also. So from these relaxation curves, as for example, the CPMG signal here, it's possible to separate some components of relaxation times of our system. For example, in plants or in many agricultural samples, we have oil and water in many situations with different T2 relaxation times. Your CPMG decay will look just like this, where you can see that here we have a shorter component and a component with longer relaxation time. And so processing this signal using some fitting method, for example, the inverse Laplace transform, you can obtain a spectrum of the distribution of relaxation times, where this peak here represents this fast decay here in the CPMG, and this second peak, the longest decay. So, as it is the case in many situations. So, the water and oil molecules can have different relaxation times because of the interaction with different chemical components in your sample, but also it depends on the conditions of the porous media that it is. For example, in this situation, if you have small pores, the relaxation times are very short. And then if you have big pores like this, this picture I try to show you. So when you acquire an NMR signal, you acquire every signal together, as you see here from this situation. Then you need to use some fitting method or some inverse Laplace transform method to obtain the distribution of the relaxation times that you have and correlated it with the properties of your sample. So this same approach we can use for foods or any other materials. For example, for I'm showing here in fruits or meat or, and the thing is that we always try to correlate the change in the relaxation times spectrum with the structure or the chemical environment in the sample. For example, in ripening or injury of some food or the sugar content in some sample or oil content, protein, and these macroscopic properties we can correlate with the relaxation times. During the workshop, we will see many applications and many situations that use these methods. So there are a lot of methodologies well established in the industry as fat oil content, moisture content, and there are a lot of methodologies that are already used a lot by the industry, but also, and especially in Brazil economy, there are several different applications that need to be developed and calibrated, mainly in the agricultural context, for example, oil industry and many others. Great, so we saw an overview of NMR spectroscopy and relaxometry methods, and now we can discuss some aspects about the instruments. All the instruments are mainly made of three parts: a computer to control the experiment and data analysis, a spectrometer which have all the necessary electronics to apply the radio frequency pulses, amplify the signals, digitalize the signals, and the magnet where we introduce our sample to be analyzed. So just to illustrate, here we can visualize some equipments of magnetic resonance imaging. And here I show you a representation of a high resolution NMR lab with the computer, the NMR console, and here the superconductor magnet, where we insert our sample in the middle of the magnet. If you look inside the superconductor magnet, in this kind of equipment, we do not have permanent magnets. What we have are superconductor solenoids that need to be at very low temperature to work. So they are immersed in cryogenic liquids to produce a high-intensity magnetic field with high homogeneity and stability just in the sample position. So to keep the solenoid in its very low temperature, it has a chamber of liquid helium, liquid nitrogen, a vacuum chamber, and to keep all this working, it is very expensive, all right? So comparing these traditional chemistry NMR laboratories with the benchtop equipments, of course, the strength, the homogeneity, the stability of the superconductor magnets are much better and are needed for applications in very complex sample, like biological samples, solid state materials, nucleus of low sensitivity, and many other scientific techniques. However, there are many new types and variations of equipments for different industrial or scientific applications, from low-resolution equipments, imaging equipments, and even spectroscopy equipments, like with these newest versions of benchtop NMR that have an intermediate magnetic field of 1 to 2 Teslas that are not as big and as expensive than the traditional high-resolution NMR instrument, but also has the power of chemical analysis with the spectrum, with an intermediate spectral resolution. So these equipments are opening a window of opportunities for many industrial, scientific, and industrial applications. Here, I'm just showing you some equipments of low resolution with the relaxometry methods, and these benchtop equipments with this potential to do spectroscopy and also relaxometry analysis. For example, in the topics that we will see in this workshop for food quality control, pharmaceutical and cosmetic analysis, polymers, and a lot of examples that we will see in this workshop. So, the very fast talk here, there is a vast literature about the topic we discussed, with many of the illustrations that I used in this talk are in this reference. So, okay, I talked very fast, the time was very short. So thank you very much. I hope I could provide in this first talk a fast but a nice overview about the main aspects of low-field NMR equipment, theory, and some applications. Here you have my mail, if anyone wants to contact me. And also for the students, I have a YouTube channel where I have some videos, mainly in Portuguese, about processing NMR signal, like with Fourier transform, inverse Laplace transform, and other videos about low-field NMR. There's a link here. So thank you very much. I'm open for questions and we can talk.
Thank you very much, Tiago, for the nice talk, an overview of the theory of NMR, for those who never had in contact with that. And I think I have, do you have any questions from the audience? No? So I'll go to the chat. I think we have one. The question is from Wolfgang Killen, I think his name, CPMG, how to deal with imperfect 180 pulses due to B1 inhomogeneity across the sample? That's the question.
That's a great question. Let me think. I'm not sure how to answer this question. I know that CPMG is it's a powerful technique to deal with this B1 inhomogeneity, but I'm not sure when you ask how to deal with it, if it is introducing some, if your magnetic field is very inhomogeneity, and if your coil has a very inhomogeneity B1, this can be a problem, of course, but I'm not sure how to answer your question, how to deal with it. Sorry, yeah.
Okay, let me see if hands up. Is there any hand up?
Colnago?
Answer that. No, then CPMG, what he does, if you collect only the certain type of echoes, not only the 1, 3, 4, only 2, 4, 8, and this inhomogeneity is compensated because you turn just 180 degrees around the y-axis. After the first one, you have some problems with D1 inhomogeneity, but when you reverse the 180 degrees, you have the same imperfection that go to one direction and you return the second direction. Then the signals that are, for example, 2, 4, 8 echoes, they are always compensated that problem with D1 inhomogeneity, okay?
Great.
That's the way CPMG works, yeah? For example, you can use, for example, 9-degree pulse. We still have a very good CPMG decay.
Okay.
Thank you, Collabo.
Thank you, Collabo. Yeah, I think that's a great answer.
Okay, I have one myself, if there is no other question. How do you see the development of low-field NMR and nowadays in terms of development of new pulse sequences? And how straightforward is to introduce new sequences on the commercial equipments?
Okay, I see that in the scientific literature about new pulse sequences in these new low-field equipments and even in the old low-field equipments, the electronics of the system are evolving very fast. So the possibilities to implement different types of pulses and with not only changing the times and the amplitude of the pulses, open very many new possibilities in this field. So that's why we have so many works in the literature about new pulse sequences for solid materials and for other materials that we typically have problems in low field equipment. So this was the first question, and the second part of your question was
how straightforward is to introduce these new sequences in the commercial?
I think it depends on the company. It depends on to do some collaborations with the
ela tá por aí.
Sorry. And I think it's easier. For example, I know that the Bruker has the top spin software for the high resolution NMR equipment, the high field equipments, and he's using the same software for the benchtop equipment. So you can use the same pulse sequence and programming the pulse sequence in the same language. So I think this is a good idea because it's very easy to use both. And yeah.
Okay, thank you. Any other questions? I don't see any on the chat. And I don't see hands up. So thank you, Tiago, again, for your nice talk. And
thank you, Sonia. Sorry for a very fast talk. I was a little nervous, but thank you very much to all the organizing.
Okay, while you are unsharing your screen,